All right, so today we're going to be finishing up chapter 21. We're going to be talking about the electric fields of extended charge distributions now. So before we get into that, I just want to quickly go back over what a test charge is, because this pops up a lot, and especially I think in 7LD, you'll get a lot of questions on test charges. So a test charge is just an imaginary positive point charge. It's not always imaginary, but it's always positive. Whenever you see test charge, immediately assume it's a positive point charge. And all it does is it kind of just tells us where the lines of the electric field are. So remember, the electric field line, let's say we have some kind of weird charge distribution that has electric field lines like that. And our electric field lines are kind of wavy. If we put a positive point charge right here, it would follow this electric field line that you put it on. Or if you put the test charge right there, it would follow the field line that goes through that point. So test charges are just a way to test where the electric field is, what the electric field is like in a region, what the electric field lines look like, since a positive charge will move along those electric field lines. Okay, so now let's talk about extended charges. So extended charges are kind of what they sound like. They're charges that are extended in space. So we talked about a point charge already, where a point charge is zero dimensional because it's just one point, right? One point has no measurements. You can't measure how big a point is. It's zero dimensional. So now we'll be looking at charges that extend into 1, 2, or 3 dimensions. So there's a couple of like vocabulary and notation that we need. So let's say we need the symbol, we need the quantity it measures, and we need the dimension. So when we talk about extended charges, there are certain symbols that you'll see over and over, and they usually refer to a specific thing. It's not like a perfect convention, but 99% of the time when you see these symbols, they will refer to the things we're about to talk about. So the first one is a point charge. So normally when we talk about a point charge, we call it Q or capital Q. So this is a point charge. And this is zero dimensional. Now when we get into extended charges, we'll see our first extended charge is a line charge, and that will be represented by lambda. So lambda refers to the charge density of a line charge. So that is going to be the charge per unit length. Or another way to think of that is the total charge divided by the total length. So if I have, let's say I just have a line in, whatever, on the x-axis or something, it has length L and total charge Q. Lambda for this line charge would just be Q over L. It's the charge density of this line charge. So lambda almost always refers to the charge density of a one-dimensional line charge, and line charges are one-dimensional. They're infinitely thin, and they just extend in one direction. Okay, then the next one is sigma. So sigma you will see referred to for surface charges. So this is the charge per unit area. So it's a surface charge density, or the total charge divided by the total area. So if you have like a sheet, we'll be doing infinite sheets today. So if I have like an infinite sheet of charge that, let's say, extends infinitely far in the y direction and infinitely far in the x direction, that's 2d, and it's infinitely thin in the z direction. So our sigma will refer to a 2d surface charge density. And then lastly, we'll have rho. So rho refers to a three-dimensional extended charge. It is the charge per unit volume, or the total charge divided by the total volume of whatever we're looking at. So we'll be doing charge spheres probably tomorrow, if not definitely Thursday. We'll be doing charge spheres, and we'll be using rho to denote the density of charge in that sphere. So you take the total charge of the sphere, divide it by the total volume, you get the charge density. And this is three-dimensional since it's a volume, a charge per unit volume. So now we can talk about how to calculate the electric field of these extended charges. So remember from yesterday that the electric field obeys a superposition principle because it's a vector field and vectors just add. So if I wanted to find the electric field of a charge distribution like this, where we had 3 point charges, we know how to find that. We just add up the contribution from each one. So in this case, we would have the total electric field is just the sum of the individual electric fields, right? You just sum over it. Now, if I have, let's say, a lot of charges, so let's say I have like 20 charges or something, you'd still have to sum over 20 electric fields. But any continuous charge distribution, you can think of as infinitely many point charges together. So if I had a ring, so let's say instead I had a ring of charge, or half ring this is, so if I had like a half ring of charge like this, you could think of this as infinitely many individual point charges. And if you have to add up infinitely many infinitesimal things, that sounds kind of like an integral, right? So for our extended, charge distribution, our sum is going to become an integral, and we're going to be integrating over the charges. All right, so we have an equation for this. So if we have some general continuous extended charge distribution, we want to find the electric field for that at some point. We're going to have to integrate over the charge distribution. So let's go over this point by point. So our electric field is still a vector. We have the 1 over 4 pi epsilon naught. So this looks almost exactly like our electric field for a point charge, except now we have this dq. So instead of just having q, it's a differential element of charge, dq. We're integrating, and we still have the r squared, and we still have the r hat. So dq, like I said, is an infinitesimal point charge in your extended charge distribution. R, again, is just the distance from that infinitesimal dq to whatever point you're measuring your electric field at. So let's say I have some weird shape like this, and I want to find the electric field out here. My R would be from each point in this charge distribution. I will calculate the distance from that dq, this little point charge, to the point where I'm measuring the electric field. And I will also calculate the unit vector r hat. And you're going to do that for each point in the charge distribution, and you're going to be integrating, right? So each point, from each point, you're measuring r, and you're finding r hat, and then you're going to integrate over all of those charges to find the total electric field at that point. So you're basically just summing up all of the individual contributions from each point charge in your distribution, your charge distribution. Okay, and then one thing we do have to be careful of, as we'll see when we do a couple of examples, this r hat is going to create some problems for us here. If you've taken vector calculus where you've done integrals involving r hat or theta hat or phi hat or any of the other non-Cartesian vectors, as you integrate over your charge distribution, this vector is going to change direction, right? So you can see here that as I move from point to point, the vector that goes from that point to the point where I'm measuring the electric field changes. So this r hat is actually going to change as you integrate. So always make sure when you're doing an integral that you've converted your integral to something with x hat, y hat, and z hat, because those don't change direction. X hat, y hat, and z hat are fixed directions in space, and they don't change as you integrate. So I'll show you, we'll do examples, but just keep that in mind. You don't want to actually be integrating once you've set up your integral, you don't want to still have an r hat in there or, anything besides x hat, y hat, or z hat. So let's see how this works. We'll do an example. So let's start with our 1D example, a line charge. So here we have a line charge where it's a positive, so a total positive charge Q is distributed uniformly along the y-axis from negative A to positive A. We want to find the electric field, a distance x from the origin. So this point out here is just some general point at x comma 0. And it's midway between the two edges of our line charge. So let's find the electric field. So we're going to write our equation. We've got dq, r squared, and then r hat. So let's figure out each of these separately. So let's look at dq first. So dq is our differential charge element. So since we're in a line charge problem, our dq is going to involve lambda. So our dq is lambda, which is the charge per unit length. So that's each little point, each individual point on this line has charge lambda. And then you can see that our line charge is along the y-axis. So we're going to be integrating with respect to y because that's where our charge is. So it's going to be lambda dy is our differential element here, our dq. And then we kind of know lambda already, right? We said it's the total charge per unit length. And we know our total charge is q. And we know our total length goes from a to negative a. So our total length is 2a. So the length of this is 2a. Okay, so we'll leave things as lambda for now, just so that we don't have too many variables floating around our integral. But just keep in mind that we do know what lambda is. It's q over 2a. Okay, so let's plug that in now. So we have the 1 over 4 pi epsilon naught is not going to change. We have lambda dy. Now we have to find r. So r, let's look over here. So what we want is the distance from each point along our line to this point where we're looking, where we're measuring the electric field at. So let's start just up here. Let's just choose that top point at y is equal to a. So r is going to be this distance. And we can just use the Pythagorean theorem here, right? Because here we know that r makes a triangle clearly. This is a right angle over here. And this distance over here is x, right? Whatever this point is, this length is going to be x. And then this length here is a, because we go from y is equal to 0 to y is equal to a. So this length is a here. So we can just say that r is equal to x squared plus a squared square root, right? So that's our distance there. All we do is the Pythagorean theorem. And now that's only true for this top point, right? But I have to integrate along this entire thing. So I have to figure out what is the distance r for each point here. So let's look at a different point. So if instead I choose some random point, let's say here, and I want to know the distance to here. Well, we still have a triangle, so we can still use the Pythagorean theorem. So now we're at some position 0, comma y, right? Because this point here is at some position y along the y-axis, so its coordinate is 0, comma y. So now I can just use the Pythagorean theorem again because I still know that this side is length x and this side is length y. So I can just swap out this a here for a y. And now this will be true at any point along my line charge here. The distance from any point along this line to this point along the x-axis is going to be x squared plus y squared, square root. And obviously you can do the same triangle down here and the negative won't affect anything since it's squared. So now I know what I'm going to put here. I'm going to put, for r squared, I have x squared plus y squared, because don't forget we're squaring the square root, so it just becomes x squared plus y squared. Okay, now the hard part is this r hat vector. So what am I going to do about this r hat vector? So let's look back at our top point here. So let's go back to this top point, oops, at A, and figure out what r hat is there. So we're back up here. R hat is going to be in this direction. And let's just extend it down this way, right? I can just kind of, remember, you can move vectors around, put them wherever you want. The important thing is that the direction doesn't change. So let's just extend that vector a little bit so that we know what direction it's pointing down there. Now, let me get rid of this so it's clear. Now, you might think, okay, well, I just have to figure out what direction that's in. And for the point at, y is equal to a, that's fine, you can. But don't forget, you're going to have to integrate over all of the points here. So at each point, this direction, r hat, is going to change, right? R hat here is a different direction than r hat over here, and is a different direction than r hat over here. So what's a general way that I can write this in terms of x and y so that I can do my integral? And you're going to have to be a little bit, you're going to have to cheat a little bit and make some symmetry arguments. And as we'll see in our next chapter, symmetry arguments are super important. Knowing when you can sort of cancel things out and cheat a little bit in your math by seeing that a problem is symmetric is going to save us a lot of time. So what I see here is I have some vector going this way. So that means that the electric field, due to this top point here, is going to be pointing in this direction. So if I just consider this point up here, what direction is the electric field over here caused by this point up here? It's going to be in the r hat direction, right? Because that's how we define the direction of the electric field. So it's going to be pointing in this direction. But the electric field created by this point at this point is going to be like this, right? So let's just change those because we're talking about which direction is the electric field in to think about this. So let's extend that. So the electric field, due to these two charges, we can kind of see it's going to cancel in one of the directions, right? So if I look over here, these two triangles, if I want to make a triangle like this and a triangle like this, these two triangles are going to be equal. Because if I break them up, if I break up this vector and this vector into the x and y components, we'll see that the y components are equal and opposite, right? Because since this is exactly the same length, since this rod is symmetric about the x-axis, this component over here and this component are going to cancel. So our y component of the electric field is going to cancel. So let's do EY will cancel. And you can see that that's going to be true for every single point along this rod. If I choose this point, and the electric field is going to point like that, it's going to have a corresponding point, just opposite it across the x-axis, going like that. And again, your y components are going to cancel. So these y components here, we can break each one up so we have x and y components. These y components are in opposite directions for every single point along this rod. And then the x components we see don't cancel. So the x components will add for each point along this rod. The x component only will contribute. And the y component will be canceled by its sort of mirror image point charge over here. All right, so we know EY will cancel and only EX will be left. So how do I find EX? So what I want to do is, instead of writing like an equation for r hat, I want to just figure out how do I just pull out the x component of my electric field. Because once I do this integral, this is going to be the magnitude of my electric field. And I want to just pull out the x component of that. So how do I get the x component of a vector? Well, since our vector, we can call this angle theta. If I want to find the x component, that's going to be the cosine, right? X here is adjacent to my theta angle. So I want to just find the cosine of this, because like I said, this is the magnitude. I just want to pull out the x component of that. I know it's going to be pointing in the x hat direction because I said only the x components will be left, the y components will cancel. So I want to just put, a cosine there. But cosine doesn't really help my integral yet because I'm integrating with respect to y. So I don't know what theta is yet. So how do I get theta in terms of things that I do know, basically x and y? So let's look at this triangle again. Now, if you think back to like your intro, like geometry class or something, you can see that since I just extended this vector through here, this angle and this angle are going to be congruent. So this is also theta over here. Now, I don't really know anything about this triangle over here, but I do know things about this triangle, right? I know things about this triangle here. I know that this side is a length x, right? Because we're just going out to some point x here. And I know this side is length r because that's how I defined r, right? So now I can write cosine in terms of x and r. So let's write cosine theta is equal to adjacent over hypotenuse. The adjacent is x, the hypotenuse is r. So now I have cosine theta is equal to x over r. So I can replace cosine theta with x over r. But I don't want to include r in my integral because I'm integrating with respect to y. I want to include x and y. So let's replace this r with x and y. So I'm going to rewrite cosine theta is x over x squared plus y squared square root. So now at every single point along this rod, whether we start up here or we look at a point over here, I now know the cosine of that angle, and it's given by this. So now for every single point along my rod, I can pull out the x component. So now let's rewrite this in terms of what we have. So we have 1 over 4 pi epsilon naught. We're integrating lambda x squared plus y squared. I'm just going to keep the dy for the end. And then I'm replacing cosine theta with x over x squared plus y squared square root. So now I have x squared plus y squared square root. And then I have dy, and then this was all in the x hat direction, we said, since it's only the x component. And then we're integrating, I forgot to mention earlier, we're integrating from negative a to a, since we're just integrating along this charge distribution. So our limits of integration are going to be negative a to positive a. All right, so let's clean this up a little bit. So let's do this. Okay, so let me rewrite this equation so that it's a little bit clearer. So I'm going to write x lambda. So I just switched my x and lambda because it just looks nicer. So now here I have x squared plus y squared, and then I have x squared plus y squared square root. So if I have an x squared plus y squared to the power of 1, right, this whole denominator here is raised to the power of 1. Oops. And then my square root, remember you can write the square root as the power of 1/2. I can rewrite this as x squared plus y squared to the 3/2, right? Because I have the power of 1 and the power of 1/2. So I can rewrite this as x squared plus y squared 3/2. And then I'm integrating with respect to dy, and this is in the x hat direction. All right, so now I'm ready to do my integral. So it's important to just understand here why, like I said before, I had to switch into x hat instead of leaving an r hat in my integral. So we can see now that as we integrate along this rod, the direction of r hat changed. So if you leave an r hat in your integral and you just have it as r hat, you're not capturing that change in r hat. So we wanted to rewrite our integral in terms of a vector that does not change direction as we integrate, right? X hat stays x hat no matter which point along this rod we're at. And then we wanted to just rewrite our integral in terms of x's and y's. All right, so now I'm just going to copy this. And let's make some more room. So, okay, so this is our electric field. Now, I'm just going to rewrite this with all of our constants outside. So we just took lambda out, and then we're left with just this. Now this is not an integral that I would expect you to do on an exam. I think you need a trig substitution to do this one by hand, and I don't need you guys to do a trig substitution. So if I gave you something like this on the exam, I would just give you the integral. So integrals of this form, where it's x over x squared plus y squared 3/2, and then with respect to dy, this is just equal to 1 over x y x squared plus y squared to the 1/2, and then evaluated at the endpoints. So I would just give you what this integrates out to. Okay, so now we can just plug in our limits of integration. So our constants, let's keep out here. So our limits of integration, we still have 1 over x. Y is a in the first one, x squared plus a squared to the 1/2. And x is a constant out there. And then we subtract negative a x squared plus a squared to the 1/2. We have a minus minus, so we can just make this a plus. And so this becomes 1 over x, and then we have 2a x squared plus a squared to the 1/2. Okay, so now we can just rewrite our final answer. So remember we had a lambda over 4 pi epsilon naught. So let me just rewrite that. So we had the electric field was lambda over 4 pi epsilon naught, and then we had a 1 over x. We had a 2a x squared plus y squared 1/2, and this was all in the x direction. Now let's just replace lambda with our q over 2a, because you don't want to, when you do any problem, you only want to use variables that they gave you in the problem. So since the problem didn't mention lambda, you want to just put it back in terms of q and a and negative a. So let's just replace lambda with q over 2a and then simplify things. So we have q over 2a, we have our 1 over 4 pi epsilon naught, we've got a 1 over x, we've got another 2a, x squared plus y squared 1/2, x hat. Okay, so we can see that our 2a cancels over here, and then we can just rewrite this. E is equal to 1 over 4 pi epsilon naught q over x, and then we have x squared plus y squared 1/2, and this is in the x direction. Okay, and then this is e of x, since we're looking at some point. We solve this for some arbitrary point along the x-axis, so our electric field is just e of x. And this is our final answer. All right, so now let's go on to another problem. So here we have a charged ring. So we have a total charge Q is distributed uniformly over a ring of radius A. Find the electric field along the center axis of the ring a distance x away. So we're doing the exact same thing where we're choosing some, at whatever arbitrary point out here on the x-axis, the ring is centered so that the x-axis goes straight through the center, and it has a radius of a fixed radius of a. And we want to find the electric field out here. So let's write down our electric field equation. We've got dq, r squared, r hat. All right, so first thing, let's start with dq. So here, dq, it's sort of still a line charge even though it's in a ring, right? We can simply just like unwrap this and it will still be a one-dimensional line charge here. So we're still looking at a line charge even though it is shaped in a circle. So let's say lambda. And then how are we gonna sort of quantify the fact that it's in a circle? So what we're gonna do is we're gonna integrate around the circle. And let's call that variable of integration ds. So what we're doing is we're just going to integrate like in this direction around this circle, and we're going to call that variable of integration ds. So you can call it anything you want. If you want to call it like dv or dl, dr, whatever you want to call it is fine. So we're integrating around there. So what is lambda? Lambda is the charge, the total charge divided by the total length. So the total charge we know is q. And the total length we're going to be integrating over, we're integrating over an entire circle. So that's just the circumference of a circle we're integrating over. So the length is going to be 2 pi a, which is just the circumference of the circle. Okay, now let's find r. So let's write what we have so far. We've got 1 over 4 pi epsilon naught. We've got lambda ds. And now we want to find what is r. So let's start at some random point up at the top here. R is going to be this distance, right? So what is r in this case? Well, we have a triangle again, right? So we've got a triangle here. So we know the length of this side already is x. And then we also know the length of this side, right? It's just the radius of the circle, which is a. So we can just write r is equal to x squared plus a squared square root. And now luckily this won't change as we go around the circle, right? Because the radius of the circle, isn't changing. So as we move around this circle, the distance from anywhere around the ring is still going to be x squared plus a squared, since the size of this triangle, the length of the hypotenuse here is not changing, since neither of these two sides are changing either. Okay, so now we can put in the denominator, we've got x squared plus a squared. So now we need to figure out r hat. So r hat is going to be in this direction, same as the direction we drew here. So r hat is going to be in this direction. And now we can see that sort of the same thing is starting to happen as happened in our previous example. The electric field, so let's just say the electric field, due to this infinitesimal charge up here, at this point down here, is in this direction, right? It's in the r hat direction. So it's in this direction. So if I just extend it out a little further over here, I can see that it's just going to go like that. So this is the electric field due to that top point over at the top of my ring. Now, this charge up here has a corresponding charge down here that's going to have an electric field contribution in that direction, right? And then if I extend it out, it looks like that. So now we can see that sort of the exact same thing is happening as we just saw, where if I break this up into components, my y component, I'll call this EY, my y component is canceled out by the y component from the charge on the other side of the ring. So again, my y components are equal and opposite since the ring is symmetric. And only my x components are going to contribute. So only the x component over here will add up. So again, now I'm just going to pluck out the x component. This is going to be my magnitude, my electric field magnitude at this point. And I want to just pluck out the x component. So I'm going to have, again, we're going to use that cosine theta trick since the x component will be the adjacent side. This is our angle. This is the adjacent side. So this angle theta will be the same as this angle theta. And then we can just use this triangle here. And we can say, all right, well, cosine theta, so for any point we choose along the ring, this angle theta is going to be the adjacent. Adjacent is x divided by the hypotenuse, which is going to be this distance r, x over r, and we know what r is. We know r is x squared plus a squared. So if I want to just pluck out the x component with cosine, I can just replace cosine theta with this. So let's rewrite that. So we've got 1 over 4 pi epsilon naught integral. I'm going to save the ds for a second. And then we've got x squared plus a squared, again, to the power of 1/2. So I can, just as before, combine these into a denominator of 3/2. So let me just rewrite this. So we're going to have x lambda over x squared plus a squared to the 3/2. And this is integrated with respect to ds. And then we said this is our x component, only is still there. Okay, and then I just have to fill in my limits of integration. So we said we're integrating around the whole ring, right? So we're integrating along this strip, and we're integrating from the length starts at 0, and it is the whole circumference of the circle. So we're integrating just over the length of that circle, which is going to be 2 pi a. So we're just integrating from 0 to 2 pi a, since that's the length of our circle. Now you can see here, so let me just copy this, that our variable of integration is s, but there's nothing that depends on s in this integral. So everything in this integral is a constant, right? And there's really nothing to integrate. So I can pull all of this out of my integral and have 1 over 4 pi epsilon naught x lambda x squared plus a squared 3/2. And then I'm just integrating ds from 0 to 2 pi a. And what is that? Well, that's just 2 pi a. So there's really nothing to integrate. So I can now rewrite my equation here. X lambda x squared plus a squared 3/2, and then I just have a 2a tacked on at the end. And now I can do the same thing I did before and replace my lambda with q over 2 pi a. So let's replace lambda with 2 pi over, q over 2 pi a. So q over 2 pi a. And now we can see that some things cancel, right? My 2 pi a and my 2 pi a from the integral cancel. So I'm left with the electric field at some point x is 1 over 4 pi epsilon naught q times x over x squared plus a squared to the 3/2, and that's in the x direction. Okay, and that's our final answer. So the electric field, again, is only in the x direction. All right, now let's go on to a slightly more challenging example. So now we have a surface charge density of a uniformly charged disk. So we want to find the electric field at some point x along the x-axis of a uniformly charged disk with uniform surface charge sigma. So that means the charge per unit area is sigma, the charge density is sigma, and fixed radius r, a distance x from its center. So again, the x-axis goes straight through the center of this disk. and we want to find the electric field out here. So first thing we're going to do, as always, is write our equation. All right, so let's start figuring out what dq is. So what is dq? Well, we have sigma, so we know it's going to be at least sigma, right? Because we're integrating our infinitesimal charge is our surface density sigma. So now what we're going to do, since it's not a prerequisite to have seen integrals using cylindrical coordinates, we're going to break it up into a bunch of little rings, and then we're going to integrate over those little rings. So what I'm going to do is say that my disk is made up of a bunch of little rings. So imagine an infinitesimal number of little rings making up my disk. And each infinitesimally thin ring has a total charge of sigma times 2 pi r. So whatever the radius of this little thin ring is, that's r, little r here, the total charge along this ring is sigma, the surface charge density, times the length of this ring, which is just the circumference is 2 pi r. So each little ring is going to have total charge sigma 2 pi r. And then what I'm going to do is integrate with respect to r. I'm going to integrate over the whole disk from radius 0 to radius capital R. And that will capture all of the charge of this disk. So I can write dq as sigma 2 pi r dr. And now if you've seen integrals with cylindrical coordinates, you can kind of see that if you do cylindrical, you'll get the exact same answer. But we'll do it this way since that's not a prerequisite for the course. Okay, so now I have dq. So what is r now? So r is going to be, let's look at the top point again. So we have some top point over here. What is the distance to this point that we're measuring the electric field? Well, at this top point, it's easy. We can see that this side, we're going to have another triangle. So let me get rid of these so that it's a little bit easier to see. I'm going to have a triangle again where this side is x, this side is the radius of my disk, and then a little r is just that, right? But this is only for the top point here, right? When I'm at the maximum radius here, capital R, I'm going to plug in capital R here. But what if I'm at a point over here? So what if I'm at some point there? What is R then? Well, it's going to be, this side stays the same, right? X stays the same. But now I'm going to have a different length here. So this is a little bit confusing because now we kind of have two r's that we're using. We're using r, the length from the charge to the point we're measuring, and then r, our radius that we're integrating with respect to. So I'm just going to call this r prime, just so that it's clear that this is our variable of integration, which is distinct from the distance between the point charge and the measurement point we're looking at. So what I want to just change here, so from any point on my disk, this distance r will just be x squared plus this length here, r prime squared. And you don't have to call it r prime, you could call it, you know, if you want to call it like s or whatever, that's fine. Just as long as it's clear that these are two different r's we're looking at. One's a variable of integration, and one's just a distance for our equation here. Okay, so now I can write my electric field this way. So I have sigma 2 pi r prime, my variable of integration, over x squared plus r prime squared. and then that's all squared. And then I have dr prime. And now, again, how do I pick out, how do I deal with my r hat? So you can kind of guess that the same thing's going to happen again, where our y components are going to cancel, our x components are going to be the only things that's left. So you can draw your vectors, your electric field or your r hat vectors for this setup, and the exact same thing is going to happen. You're going to see that if we extend this vector out here, there's going to be a corresponding point here with an electric field that goes like this, and our y component will cancel, and only our x component for each point in the disk will contribute to the total electric field. So only this x component, and again, you'll be left with the theta and the theta, and then you can rewrite, we'll have theta. It's exactly the same argument as before. You can just rewrite, we're going to want to pluck out our cosine theta there. We want to pluck out the x component. We can write cosine theta as adjacent over hypotenuse, which we said is x squared plus r prime squared. It's a different r, remember, our variable of integration. And then we can just replace cosine theta now. And we said this is all in the x hat component, sorry, the x hat direction, since our y hats cancel, and you get a 0. And you get no electric field in the y direction. Now, one thing you can actually do for all of these is you can, if you want to prove to yourself that the y component really does cancel for all the problems we've done so far, the y component is going to be given by sine theta here. So you can write sine theta, figure out how to write sine theta in terms of our variables, write sine theta, and then actually do the integral. And you'll see that in each case we did, where we sort of just made a symmetry argument that the y component has to cancel, you'll see if you actually replace this with sine theta and follow the integral all the way through, it will end up being 0 anyway. So even if you want to test it out, that's like a good test to make sure that you understand how to set up these integrals and see that you really do get 0 for your y component. So either way you do it, whether you make a symmetry argument or you actually calculate the full thing, you'll get 0. Okay, so now let's rewrite this here. So we've got 1 over 4 pi epsilon naught sigma 2 pi r prime x squared plus r prime squared. And then we have our cosine is x squared plus r prime squared square root. And then this is all dr, and that's all also in the x hat direction. Okay. So also, we just need to write our limits of integration. Remember, we're integrating all these little rings from 0 radius all the way out to capital R radius. So our limits of integration are from 0 to capital R. Okay, so let's just clean up this integral a little bit. So we'll have 1 over 4 pi epsilon naught. We're integrating from 0 to capital R. We have sigma x 2 pi r prime x squared plus r prime squared to the 3 halves, same thing as before, and then we're integrating with respect to dr prime. Okay, so let me write this on the next page. Okay, so now to solve this integral, let's move some of our constants outside the integral just so that we have a little less clutter. So let's move our sigma and our 2 pi outside here. So let's put sigma and 2 pi out there. And so now we just have x and r over here. Okay, so how do I solve this integral? Unfortunately, you're going to have to do a u substitution. Now, there's I think only 2 instances in this class where we do a u substitution. They're not, like I said, they're not like trig u substitutions or anything like that. Very straightforward u substitutions. So let's go through that. So what we're going to have to do is we're going to call our denominator down here, our x squared plus r prime squared. That's going to be our u. So u is x squared plus r prime squared. That means du is, x is just a constant in this case, right? Because we're integrating with respect to r, and in this case now we're differentiating with respect to r. X is just a constant. So du is just 2r prime dr. So now I want to replace, if I see a 2r prime dr, I want to replace that with du. And I do see a 2r prime dr, right? I have a 2 over here, I have an r prime, and I have a dr prime. Oops, I should have dr prime there. So now I can replace everything in this integral. And remember, x is just a constant here. So it's okay that I'm going to have an x left when I do my u substitution because x is just a constant for this scenario. So I'm going to integrate. Let's just integrate. We're going to have a sigma pi 4 pi epsilon naught, and we're going to have an x left out here. And then I'm just going to integrate du over u to the 3/2, right? So I pulled out x is a constant in this case since it's not our variable of integration. So I just pulled out and wrote all my constants over here, and then I just transform my integral into terms of u. So this is my u, so it's just u to the 3/2. Now, to integrate du u to the 3/2, you can use the power rule for integrals, which in case any of you forget how to integrate anything with a power, it just looks like this, where in our case, n is equal to negative 3/2, right? Because whenever you have something with a power at the bottom, it's just a negative. So in our case here, n is negative 3/2. So when we integrate u to the negative 3/2, we just get u to the negative 3/2 plus 1 over negative 3/2 plus 1, which gives us u to the negative 1/2 over negative 1/2. So let's replace this now. So we've got a 1 over negative 1/2, which 1 over negative 1/2 is negative 2. So let's replace this with negative 2. And then we have just a 1 over u to the 1/2. So now what I can do, I'm just going to replace u with my original function here. So let's rewrite all of our constants that we had outside. We had x, we've got a negative 2, and now we have 1 over x squared plus r prime squared to the 1/2 now, and we're evaluating it, since we plugged back in our original variables, we're evaluating it from 0 to r. So we're evaluating this from 0 to r. So let's plug in first, so we'll do this here. We've got 1 over x squared plus capital R squared, square root, and then minus 1 over x squared plus 0, because when I plug in 0 into r prime, it's obviously 0. So I just have 1 over x squared, square root, which is just 1 over x. So I've just got 1 over x there. And now I've got all of these constants I can worry about. So we have sigma, pi, 4 pi, epsilon naught, we've got x, and we've got a negative 2. So let's just rearrange some things. Let's distribute out this negative 2 into here. So that will give us, and let's cancel our pi's. So our pi's will cancel. Let's distribute out this negative and this x. So we will get, outside we'll have sigma over 2 epsilon, because this 2 and this 4 will cancel to just a 2. And then we'll have, okay, so we've got sigma over 2 epsilon. We've got a negative we're distributing to over here, which will give us a positive. And then we have an x, which we're distributing out over here. So we're just going to have 1 minus because now we're distributing this negative to this term, minus x, since I've distributed this x now over here, over x squared plus r squared square root. All right, and then this is all in the x hat direction, and that is our answer. So this is our electric field, some distance x along that center axis. Okay, so this is probably the most difficult kind of integral we're going to do, where you have a u substitution and you have to do an integral like this. So yeah, no trig substitutions for integrals. This is as advanced as we're going to get for this type of stuff. Okay, so I know there's a lot of tedious, like distributing negative signs and everything. So just work through it yourself. Make sure you understand how I got here. And definitely review some basic u substitutions and your basic integrals like this. Okay, so now let's move on. We have like 1.5 more examples. So now we want to look at an infinite sheet. So I mentioned before we're going to do an infinite sheet. So an infinite sheet, let's say I've got the z direction, and then I've got my x and y directions over here. So let's say I have a sheet, so I'm just drawing here a little piece of it, but pretend I have a sheet that's charged. Let's say it has a positive surface charge sigma, and it extends in all directions. So I obviously can't draw something that extends for infinity, but pretend this sheet is in the xy plane, and it extends out to infinity in both directions, and it's infinitely thin. So if you look at it sort of like head on, if this is your z-axis, this is, let's say, your x-axis, it's just extended like that. It's just right along your axis there. Okay, so what is the electric field of this? Now we're going to do this when we do chapter 22. We're going to do this in a more simple way. But one thing you can do is you can see that if I did this exact integral again, and I extended my radius, if I had a disk and I extended my radius out to infinity, that would be an infinite sheet, right? Because it's an infinitely large circle, that will look like an infinite sheet. So since we already did a disk, what you can do is come over here and take the limit of this as r goes to infinity. So I'm not going to make you do that, and I'm not going to do it either since we don't do any other integrals. But if you took the limit as r goes to infinity, so you made your disk infinitely big, what you would get is the electric field of an infinite sheet. And this actually comes out to sigma over 2 epsilon naught. And that's because when you take r to infinity, this term just goes to 0. And so you're just left with this first term here. So you just get sigma over 2 epsilon naught times 1, and then this is just 0. So, and this is in the x hat direction. Oh, sorry. So I should have drawn let's do it this way. I should have drawn my sheet along the z-axis since my electric field was in the x direction. So I should have drawn my setup like this. So let's say this is x and this is y and z. Okay, so I just flipped my axes so that it is consistent with the form that we just calculated. It doesn't really matter, obviously, what you call your axes. I'm just trying to be consistent with our previous problem. So this is the electric field. We were calculating on the positive side of the x-axis. So that means that my electric field for an infinite sheet looks like this. And you'll notice now that my infinite sheet doesn't say anything about how far away I am from the sheet, right? It's just sigma over 2 pi epsilon, and those are all constants. My sigma is just the surface charge of the sheet, so that doesn't change. Epsilon doesn't change, and x hat is just a vector, so that doesn't change. So that means when you have an infinite sheet, your electric field extends infinitely far above it, and it's constant everywhere. You just have the same electric field at all points in space, and it's given by this. Now, on the other side of the sheet, So this is a positively charged sheet. The electric field will just extend in the other direction, infinitely far. It's going to be constant as far out as you go. So this is what the electric field looks like for an infinitely charged sheet. It just goes in either direction away from the sheet. So this is for points x greater than 0, and then it will be sigma 2 pi epsilon naught negative x hat for points on the other side. All right, so this is our electric field for an infinite sheet. And again, when we do Gauss's law, we're going to see this again, so definitely keep this electric field in mind. So now let's look at what happens if I put two of these sheets together. So if I took two infinite sheets, so let's say those both go off to infinity. And let's say this top one is positively charged and this bottom one is negatively charged. I know what the electric field will look like for the top one, right? It's going to be pointing away like this. On both sides, it will be pointing away. Now, I also know what the electric field for the bottom one will look like, right? Well, it is going to look pretty much exactly the same as the positively charged sheet, but for negatively charged things, the electric field points inward. So it's going to look exactly the same, except our electric field is going to point towards the sheet because it's negatively charged. And again, you can do this exact same setup where you take a negative disk, take R out to infinity, and you will get an electric field that looks exactly like this. Okay, so now let's look at the different regions. So we can see actually that between these two sheets, the electric fields add, right? Because I have two electric fields now pointing in the same direction that both have magnitude sigma over 2 epsilon. And the only difference is that the positive and negative plates just have opposite charges, but the magnitude is the same. So since the electric field is in the same direction here, it's going to add. And in between here, I'm going to get 2 times sigma 2 epsilon naught, which is just sigma epsilon naught. So between my plates, between my infinite sheets, this is my electric field, because my electric field is just added from each. Now, out here, you might think that the electric field is given by sigma over 2 epsilon. But that's not entirely true, because you still have a contribution from this negative plate. And let's just forget that this plate exists for a second. We said that up here, the electric field for the negative plate points downward. So that means that on the other side of the positive plate, you still have an electric field from the negative plate pointing downward. It's not stopped by this, it's not stopped by the presence of this other positively charged plate. So you can see now that we have two electric fields that are equal in magnitude but opposite in direction on this side of the positively charged plate. So the electric field out here is actually going to be 0. They're going to cancel. And then the same thing is going to happen on this side of the negative plate. The electric field from the positive plate still exists over here, and it's still pointing away from the positive plate, which is in this direction. So again, we have two electric fields that are equal in magnitude, opposite in direction, and they're going to cancel each other out. And down here, you will have 0 electric field. So when you have two infinite sheets or plates that have the same magnitude of surface charge, but opposite signs, so we have plus sigma and minus sigma, you will have 0 electric field out here. In between the two plates, the electric fields will add, and you'll get sigma over epsilon naught. Now, this setup is very important. This is a capacitor, and we're going to do a whole chapter on capacitors. Okay, so definitely keep this in mind. We'll be seeing a lot more of capacitors later. Okay, so that's it for chapter 21. in chapter 21 in your book, they cover dipoles. We're not going to cover dipoles until we get to chapter 24, since it doesn't really make sense to do dipoles yet. So if you're reading through your book, just skip over section 21.7 for now, and we'll come back to it when we do chapter 24. So that's it for today. If these integrals are scary to you, don't worry. This is pretty much as bad as the integrals get. So we've seen the worst integral we're going to see already. So just practice. Make sure you understand all the steps I took. Definitely make sure you understand the cosine tricks I did and why the electric field cancels out in that y direction, and you should be fine. Okay, so that's it for today, and I'll see you guys tomorrow.